Hi everyone, I'm going to talk about the space just above one clean qubit. This is joint work with Saeed Mehraban at Tufts University. So what are we doing here? We're interested in understanding how BPP and BQP relate. And in particular, on the left here, we have BPP, which is less powerful, depending on what you think, and BQP, which is more powerful, hopefully. And the question is, what the heck is going on in the middle, right? So to answer this, people have defined some models of computation. For example, IQP, one clean qubit, NISQ, shallow circuits, and linear optics, and there are more, but for now, let's just look at these. And in particular, we're going to be focusing on one clean qubit, or DQC1, as it's sometimes called in the literature. And the point of what we're doing here is, let's say we want to separate BPP and BQP. Well, doing this would imply, let's say BPP not equal to P space. So what can we instead hope to do is understand kind of what's going on in the middle here, how do adding or taking away quantum resources get you from fully classical computation to fully quantum computation, and what sorts of algorithms can you perform in this intermediate regime where you may have noise or errors or not a complete gate set, et cetera. And there are two perspectives here that I like. One perspective is sort of a structural complexity perspective, which is, like I just said, what's kind of going on here between BPP and BQP. And in particular, we're going to focus on what's going on between BQP and DQC1. And then there's an algorithms perspective, which is sort of, suppose I have some noise in my circuit, and maybe it's a restricted noise model. In what settings will classical post-processing help me deal with this noise? So in 2016, Aronson, Booland, Cooperberg, and Mehraban introduced a model of computation, which we now call half BQP. And they conjecture that it's between one clean qubit and BQP. In this work, we give strong evidence supporting that conjecture. In particular, we give oracle separations and non-oracle separations under plausible assumptions. So let's define the model. Half BQP circuit corresponds to computation on one half of a maximally entangled EPR state. So you have a left half and a right half, and you apply a quantum circuit to one half, and then you measure both halves at the end and apply classical post-processing. And then you get your output. So you might note that if you never measure the entangled system, this is like computation over the maximally mixed state, in which case you can't really do anything. But in this case, we get to learn the purifying subsystem and apply classical post-processing. So the question here is, can we do anything with this model? And first of all, note that it's trivially contained in BQP. I can just make this circuit in BQP. So like I just said, some intuition about this model is if you don't measure the second system, you can't really do anything. And furthermore, there are no pure ancilla qubits to use as workspace, similar to the one clean qubit model. So you might be wondering, how the heck do we do anything here? And this is sort of maybe historically similar to one clean qubit, where it looks very weak a priori, but it turns out you can do some things sometimes. And to start, just to give us some intuition for what's going on here, I'm going to present three equivalent definitions of half BQP. So the first definition we've seen as computation on one half of an EPR state. The second definition is computation over a random basis state. So consider you're given a random computational basis state W. You apply a quantum circuit that does not depend on W, and then you measure and you learn what W was. And then you feed both of these into classical post-processing. And as you can see here, these two things are equivalent because we could have just moved that measurement on the right subsystem to the very beginning and measured, collapsed the left subsystem to some computational basis state W, and it would be equivalent. The next equivalent model is computation with random bit flip errors. So it shouldn't be too hard to see that the model where you compute over a random state W, random computational basis state W, is the same as starting with the all zero state and applying random Pauli X errors at the beginning of your computation, and then learning where those errors occurred at the end. This will be important later. This is sort of how we take advantage of commutation relations to show that indeed you can do things in this model. So as a recap here, we have these three definitions. For the sake of time, I will go quickly here. So let's get into results. What can we actually show about this model? So in the paper where half BQP was defined, they showed that DQC1 is contained. But we noticed actually IQP is also contained here. And this is sort of the first example of a sub-universal model that contains both one clean qubit and IQP. Furthermore, we show that all the usual problems based on Fourier sampling are in half BQP. So Simon's problem, order finding, and even factoring, which is not an oracle problem in this case. You can also obtain the correlation and polynomial hierarchy separation within half BQP. So from that perspective, despite being a seemingly weak class, you can still separate it from polynomial hierarchy in the oracle model. And since one of our goals is to help resolve this conjecture that half BQP sits non-trivially between one clean qubit and BQP, we should note that as far as we know, one clean qubit can't do these things. And now for, so these are upper bounds, and now for lower bounds, we show that a variation of Simon's problem that was introduced previously to separate NISC with BQP also separates half BQP from BQP. And furthermore, half BQP cannot obtain the quadratic speedup given by Grover's search. So in case you're not familiar with one clean qubit or DQC1, the model is you have a one clean qubit and the maximally mixed state on n qubits, and you apply a polynomial sized quantum circuit and then measure the clean qubit. For those of you who are familiar with one clean qubit, there are some facts. If you're not familiar, that's okay, it won't be important. But there's a question here, which is in half BQP, how do we simulate one clean qubit? And in particular, how do we get clean ancilla qubits in a half BQP computation? So in the top left corner here, we have the random basis state definition of half BQP. And we want to simulate a DQC1 computation with one clean qubit and some mixed state on the rest of the qubits. So what we'll do is we'll optimistically assume that our desired clean qubit is 0. And when we learn the state W, we'll find that we're correct with probability 1/2. And if we didn't get a 0, let's say, when we measured W, we just try it again. And we can try it again in parallel. So then we pick whichever run of the circuit succeeded, and that's our clean qubit. Furthermore, this gives us O of log n clean qubits using only polynomially many parallel copies. And by essentially the same argument, this shows that one clean qubit is in half BQP. So now we've shown that half BQP is at least as powerful as one clean qubit and at most as powerful as BQP. But can we show that the containments are strict? And this is what we'll spend the rest of the talk on. So first, let's do upper bounds for half BQP. For oracle results, as I said, we have all the Fourier sampling related problems are in half BQP. And for non-oracle results, we have simulating IQP, discrete logarithm and factoring outside of the oracle setting. Maybe that's exciting if you can convince yourself this is a physically realistic model. And furthermore, these tasks are not known to be in DQC1. So what's IQP? IQP is instantaneous quantum polynomial time, and it's circuits with commuting gates which are diagonal in the x basis. You can also write it as layer of Hadamard gates, diagonal unitary layer of Hadamard gates, and we're going to adopt that definition just for the sake of instruction. and we're going to show that IQP is in half BQP. So recall the bit flip errors definition of half BQP, and recall an IQP circuit with bit flip errors at the beginning. So you may already see what's going to happen here is we're going to commute the errors through, learn them, and then essentially flip those bits where the errors occurred. And if you do this, the X gates become Z gates, the Z gates stay Z gates, and they become X gates again at the end of the circuit. Therefore, once we learn W, we just flip some bits of the output, and we've simulated the IQP circuit. This same idea will get us very far. This is how we do all of the Fourier sampling things. So next, we can show that Simon's problem is in half BQP. Recall in Simon's problem, there's a secret string, secret shift, such that some function f is constant on cosets of the secret string. And the half BQP, or the BQP circuit for Simon's problem looks just like that. And you'll note it looks a lot like the IQP circuit. In particular, when we start with X errors in the beginning, they can commute through on the top because the oracle is just the identity on the first n qubits. And furthermore, they can commute through on the bottom because the oracle is just applying X diagonal XORs on the second register of the algorithm, or the bottom register of the algorithm. So all in all, again, we see that bit flip errors at the beginning are the same as bit flip errors at the end for this particular algorithm. Now, if you're noticing a pattern, that's not a coincidence. And I would say it's a good thing if you have some algorithm and it relies on Fourier sampling. You might ask yourself, is it robust against bit flip errors at the beginning? In fact, I think since this paper was made available, some people have actually noticed some algorithms are robust in this setting. Right, and it turns out actually the same thing works not just with Hadamard gates, but with the quantum Fourier transform as well over larger rings. And I'll leave the algebra to you, or go read the paper if you like. But you can believe me that if you just flip some bits, flip the bits of W at the end, you'll get it'll be the same as the BQP circuit for order finding. And note here, we've been using an oracle the whole time, but you might ask, well, suppose I could build a half BQP machine in the lab. Can I factor? And in order to do that, we have to show how to implement modular exponentiation using not too many clean ancillas. And this is not a priori obvious how to do. So let's talk a little bit about how to do that, since I claim that factoring is in this model outside of the oracle setting. And I'm going to go through very quickly, and you're going to be mad at me, and then I'm going to explain why I did that. So we take advantage of, So we take advantage of some Barrington's theorem consequences and low depth circuits, et cetera. But actually, you can forget all that. Because it was recently shown that there's this thing, quantum catalytic log space, which you can learn about soon if you like. There's a talk here on it. But turns out half BQP can simulate catalytic log space, which gives you TC1. And you can compute modular exponentiation in TC1. So the reason I did this is because in our paper, we go through something, but more recently, there's a simpler way to do it, which is nice. OK, so far we've basically said, well, if you have X errors at the beginning of your circuit, then you can do these algorithms. And these things all relate to Fourier sampling. And the errors basically just pass through the circuit to the end. So you might ask, well, can you do anything else? And turns out it's not quite so simple for correlation. It's like half a step more complicated. Correlation is a problem which was originally given by Aronson and Ambinus as a candidate to separate BQP from polynomial hierarchy. And in the correlation problem, you're given two functions and the promise that the correlation between f and the Fourier vector of g is either large or small, and you're tasked with deciding which is the case. And in particular, this problem is not solvable in polynomial hierarchy and solvable in BQP using one query. And this is the four-relation circuit. Note it looks kind of like what we've been doing with Hadamard function Hadamard, except now we have 3 layers of Hadamard gates and 2 functions. So what happens when we try to pass the errors through the circuit? You'll see the x moves to the z, and you can watch it go. And it gets stuck because we have x errors and a z diagonal gate. And we can't commute it any further, so it doesn't commute all the way to the end. Oh no, are we stuck? Have we failed? Fear not. I claim that if you measure, learn W, and then compute the inner product of W and Y, this will give you the four-relation squared value in expectation. And one way to see this is, first of all, you can just do the computation yourself and prove it or look at the paper. But a neat way to see this is we can consider taking the inner product of Y and W to be like this measurement that I've placed at the end of the circuit here. We can simulate that via this measurement. And in this case, the Z gates, again, commute backwards. And you're left with a variant of that circuit here where G is sandwiched between x to the W and x to the W. And it turns out that if you have, let's say, K-correlation circuit, and you sandwich the last function in your K-correlation with these bit flip errors, you get the same, it computes the four-relation squared value. In the interest of time, I'm not going to prove that to you. But that's some sense of you can consider commuting these errors forward, and you can also consider commuting a function of the errors backwards in your function, in your circuit, when you're thinking about designing algorithms that work in half BQP. So we're done there, if you believe me. So let's do a recap so far. So far, we've done some upper bounds in half BQP and claim that, as far as we know, DQC1 can't solve these problems. And let's work on the next step. Can we show some lower bounds or separations with BQP? And first, let's prove a bit of a claim, which is that half BQP cannot distinguish unitaries which are close in trace distance. So consider some unitary, in this case it's the identity, and consider some other unitary which is the same, but you change one entry on the diagonal. So these two unitaries I claim are very close in trace distance. In a BQP algorithm, you can just prepare the state on which they differ and check if I'm in case left or case right. But in half BQP, since we don't have control over the initial state, we can't really do this. This is some intuition for what's going on. And in particular, you can prove it by formalizing this half BQP algorithm at the trace distance between your output state for some u and some u prime, which are close in trace distance, is also small. So you'll never be able to distinguish the case where you have u or u prime. And in particular, for diagonal unitaries, this requires 2 to the n queries to distinguish that case I presented before, where you have 2 diagonal unitaries and 1 entry flipped. And we get some consequences now. So one consequence is there's this modified Simon's problem, where you take Simon's problem and you stick it in a corner of your unitary matrix. So in particular, you have 2n bits of input, and if the first n bits are all zeros, then it acts as Simon's problem. Otherwise, it's, let's say, constant. And you need to be able to set those first n bits to 0 to even access the Simon's function. And as a consequence of this claim we just showed, half BQP can't even tell, can't even distinguish, can't even access that piece of the subspace, can't even distinguish if it's, say, the constant function from this modified Simon's problem. Furthermore, Grover's search is a special case of this these unitaries which are close in trace distance. So consider my marked item being the last bit string and my marked item being the second to last bit string. It's the same case as before, basically. These two unitaries are exponentially close in trace distance. And as a consequence, half BQP cannot distinguish them using fewer than omega of 2 to the n queries. So this thing that seems actually somewhat powerful after showing it can do factoring and correlation, et cetera, cannot obtain Grover search speed up, which I think is kind of interesting. And as a recap here, what have we shown? We've shown that half BQP kind of sits somewhere above one clean qubit, can do some useful things, some powerful things, and cannot do some other powerful things, such as Grover search. Yes, and this picture on the right, I guess I should say a little bit. I should tie it back to our original goal here, which was kind of to understand BPP versus BQP by thinking about intermediate classes and how quantum resources change what you can do. And so maybe morally, one takeaway you might have here is it kind of seems at the beginning like you have this super noisy thing and you can't really do very much. But when you take a different perspective, in particular this perspective of the X errors, it turns out actually you can do things here. And so there's, I guess, back to the algorithms idea. It turns out noise doesn't always mess you up. And it especially doesn't always mess you up if you can learn what that noise is. So with that in mind, I want to turn to some future directions and open problems. And in particular, I want to highlight this NISQ complexity class. So we conjecture that half BQP is incomparable to NISQ and shallow quantum circuits. And why do we conjecture this? Well, if you're familiar with NISQ, you'll know if you have a log depth NISQ circuit, it becomes too mixed by the end to really do anything useful. So NISQ seems useful in the very shallow regime. Whereas half BQP, since it can simulate DQC1, which can do trace estimation even on polynomial depth circuits, is more powerful, let's say, in the deep circuit regime for trace estimation, or in a very specific setting where you can commute your X gates somewhere through the circuit here, which seems very different than this setting with NISQ or with low-depth quantum circuits. And if you're a little more practically motivated, you might say, well, okay, you have X errors at the beginning of your circuit and then nowhere else in your circuit. That doesn't seem very reasonable, other than a toy model to place between one clean qubit and BQP. And for you, I say, well, consider the NISQ model where you have errors between layers of gates, and then you somehow measure your environment to learn what happened in those errors. So maybe, I'm not an experimentalist, but maybe you set up a lot of sensors around your system, and you can probe sort of what happened during the computation, and then apply some classical post-processing at the end. So I pose for anyone interested this question of what happens if you define an analogous model to half BQP, but you have errors throughout the circuit whose purifying system you learn. And yeah, that's it. Thank you.
Questions?
Could you clarify again how these models subsume BPP, because it seems like they operate completely on
yes. Okay, maybe it's not worth clicking back. Yeah, so for, let's say, one clean qubit, what people often do is they define the complexity class as a BPP machine with access to a one clean qubit machine. And we do sort of a similar thing here. We say you have some classical Turing machine that can run a half BQP circuit.
Got it. Also, you mentioned that correlation square is estimable in half BQP. Do you have any idea about correlation itself, like distinguishing between correlation at least 3 over 5 and at most minus 3 over 5?
I believe the square, for like a constant gap, I believe the square value should be fine for this.
Sorry, could you say that again?
So I guess the question is sort of like if you want to push the gap, make the gap smaller. Right, because if I just square everything, it'll shrink the gap. Or it'll, if I can tolerate like a smaller gap, then squaring it should be okay.
Sorry, what I meant was 3 over 5 square and minus 3 over 5 square are indistinguishable, so...
Oh, the sign.
Yeah, the sign,
Yeah, that's a good point. I don't think the proof works for
Got it.
distinguishing the sign, yeah.
Thanks.
Yeah.
Any other questions?
Nice talk. Just a really quick question about like the interpretation of the thing. Like you're interpreting it kind of as this noisy thing, but like I mean, you prepare a big GHZ state and then you act on both halves. Everything is pure, and then you measure at the end. So I'm wondering, kind of this noisy perspective, which is I guess kind of this perspective when you take this. I don't know. You showed this other way of thinking about it, but like you have one line and then the errors and stuff. Kind of, yeah, so some interpretation. Also, in a math way, are you just doing like the Choi of the error guy? Is that what's happening?
Yeah, so one way you can think about this is sampling elements from the Choi matrix of your quantum circuit.